After studying this module, you shall be able to know about MICELLE and critical MICELLE concentration, that is CMC. You will also know about the structure and composition of MICELLEs formed by various kinds of surfactants and factors affecting shape and size of MICELLEs. Let us now understand what is a MICELLE. A surfactant, when present at low concentrations in a system, adsorbs onto surfaces or interfaces, significantly changing the surface or interfacial free energy. When surfactant molecules are dissolved in water at concentrations above the critical MICELLE concentration, they form aggregates known as MICELLEs, which have particular significance in science and pharmacy because of their ability to increase the solubility of sparingly soluble substances in water. In a MICELLE, the hydrophobic tails flock to the interior in order to minimize their contact with water, and the hydrophilic heads remain on the outer surface in order to maximize their contact with water. They are dynamic structures and are continually formed and broken down in solution. There is an equilibrium between free surfactant molecules and MICELLE in solution. This we illustrated in the figure as shown. We have a surfactant tail, we also have a surfactant head, and many surfactants combine together to form a MICELLE, and there is a dynamic equilibrium between the two. On the left hand side you are seeing surfactant monomers, and on the right hand side we see a MICELLE. This is a schematic illustration of the reversible monomer MICELLE thermodynamic equilibrium. The black circles represent the surfactant heads and the black curved lines represent the surfactant tail. A MICELLE is an aggregate of surfactant molecules dispersed in a liquid colloid. A typical MICELLE in aqueous solution forms an aggregate with the hydrophilic head regions in contact with surrounding solvent, forming an outer shell, sequestering the non-polar or hydrophobic single tail regions in the MICELLE center. Hence, the core of a MICELLE, being formed of long non-polar tails, resembles an oil or a gasoline drop, as you can see in the figure. The length of the non-polar tail, the nature and the size of the polar or ionic head, the acidity of the solution, the temperature and the presence of added salts are the most important factors determining the kind of the aggregate obtained. If those parameters are changed, it is possible to change shape and size of the MICELLEs. The number of amphiphilic molecules forming the aggregate is called aggregation number. This is a way to describe the size of the MICELLE. Schematic representation of a MICELLE in an aqueous solution. as you can see in the figure. This is an. Let us learn how micellization takes place. The micellization process in water results from the delicate balance of intermolecular forces, which include hydrophobic, steric, electrostatic, hydrogen bonding and van der Waals interaction. The main attractive force results from the hydrophobic effect associated with the non-polar surfactant tails, and the main opposing repulsive force results from steric interactions and electrostatic interactions between the surfactant polar heads, as you can see in the figure. Whether micellization occurs, and if so, at what concentration of monomeric surfactant, this depends on the balance of the forces promoting micellization and those opposing it. We can say it depends on the balance of two main effects. Number one, the tendency of the non-polar tails to avoid contacts with water, and the repulsion among the polar or charged heads, which is a destabilizing effect on the aggregation process. Hydrocarbon tails avoid contacts with the solvent molecules, pointing toward the MICELLE interior, which lacks water. Instead, the repulsion among the charged heads on the surface of the MICELLE is attenuated by the presence of oppositely charged ions. The favorable association among the non-polar tails in the interior of the MICELLE occurs through the hydrophobic interaction, which is the prevailing effect in the formation process of these aggregates. Amphiphilic molecules can form MICELLEs not only in water but also in non-polar organic solvents. In such cases, MICELLE aggregates are called inverse MICELLEs because the situation is inverted as respect to water, as you can see in the figure. In this case, hydrocarbon tails are exposed to the solvent, while the polar heads point toward the interior of the aggregate to escape the contacts with the non-polar solvents. See here in the figure, we have water in between, the heads are all in a circular and the tails are all around it. Reverse MICELLEs are able to hold relatively large amounts of water in their interior, and in that way a pocket is formed which is particularly suited for the dissolution and transportation of polar solutes through a non-polar solvent. It's high time now we learn about CMC, that is critical MICELLE concentration. The critical MICELLE concentration, that is CMC, is defined as the concentration of surfactants above which MICELLEs form and all additional surfactants added to the system go to MICELLEs. The CMC is the exact concentration of surfactants at which aggregates become thermodynamically soluble in an aqueous solution. Below the CMC, there is not a high enough density of surfactant to spontaneously precipitate into a distinct phase. On the other hand, above the CMC, the solubility of the surfactant within the aqueous solution has been exceeded, the energy required to keep the surfactant in solution no longer is the lowest energy state. To decrease free energy of the system, the surfactant is precipitated out, which can be seen in the figure. When we are going from frame 1 to 4, on increasing the concentration of surfactant in water, slowly, as you can see, a layer is formed on the surface and eventually micelles are formed at or above the CMC. You must be wondering how the CMC of surfactants is determined. So, let us learn how we determine the CMC of surfactants. It is done by establishing inflection points for predetermined surface tension of surfactants in solution. Plotting the inflection point against the surfactant concentration will provide the insight into the critical micelle concentration by showing stabilization of phases. In this plot, 3 phases can be seen, which is number 1 is very low concentration of surfactant and only slight change in surface tension is detected. As you can see, the graph is parallel to axis. In the second part, addition surfactant decreases surface tension, as you see the plot going down. And thirdly, surface becomes fully loaded. So, we see no further change in the surface tension. The graph is again going parallel to x-axis, and at the boundary of 2 and 3 is what is called CMC. Now, we will understand the determination of a surfactant CMC by using physical properties. The CMC for a surfactant can be determined by measuring physical properties such as surface tension gamma, conductivity K, that is ionic surfactants, osmotic pressure pi, detergency, etc. When these properties are plotted as a function of surface concentration, a sharp break can be observed in the curves obtained, signaling the formation of micelles at that point. Now, see in this figure, we have 4 plots. The top one shows the detergency plot. On the x-axis we have surfactant concentration. Then the second plot is the conductivity. The third plot going from left to right is the osmotic pressure, and the fourth, the lowest one, is the what is called surface tension gamma. As you can see, there are dotted lines running parallel to the y-axis, and in each of the 4 plots the curve takes a sharp change at the CMC, and that is how, by studying these physical properties, one can determine the CMC of a surfactant. Another important parameter that characterizes micelles is the aggregation number, written as capital N AGD, that corresponds to the average number of surfactant monomers in each micelle. Usually, in a micellar solution, the aggregation number is approximately constant. For a broad total concentration range, it may go up to 100 times the CMC with increasing number of micelles. However, under certain conditions, micelles can grow with the aggregation number varying with the surfactant concentration. There are some other physical properties which can also be used to determine the CMC value of surfactants, and they all show some change near critical MICELLE concentration. These properties are electrical conductivity, molar conductivity, another one is light scattering, and even refractive index can help us in determining the CMC value of surfactants. Now we will understand the shape and size of MICELLEs. MICELLEs are labile entities formed by the non-covalent aggregation of individual surfactant monomers. Therefore, they can be spherical, cylindrical or planar. In planar we have discs or bilayers, as you can see in the figure. MICELLE shape and size can be controlled by changing the surfactant chemical structure as well as by varying solution conditions such as temperature, overall surfactant concentration, surfactant composition, ionic strength, and finally pH. Depending on the surfactant type and on the solution conditions, spherical MICELLEs can grow one-dimensionally into cylindrical MICELLEs, see the diagram please, or two-dimensionally into bilayers or discoidal MICELLEs. MICELLE growth is controlled primarily by the surfactant heads, since both one-dimensional and two-dimensional growth require bringing the surfactant heads closer to each other in order to reduce the available area per surfactant molecule at the MICELLE surface, and hence the curvature of the MICELLE surface. We have surfactant self-assemblies as seen in the figure. Self-assembly of surfactants leads to a range of different structures, as we will discuss now. In A, as you can see, spherical MICELLEs with an interior composed of the hydrocarbon chains and a surface of the polar head group facing water. The hydrocarbon core has a radius which is close to the length of the alkyl chain. We have cylindrical MICELLEs, and these MICELLEs with an interior composed of the hydrocarbon chains and a surface of the polar head groups facing water. The cross section of hydrocarbon core is similar to that of spherical MICELLEs. The micellar length is highly variable, so these MICELLEs are polydisperse. In C, you can see surfactants bilayers which built up lamellar liquid crystals have for surfactant water system a hydrocarbon core with a thickness of 80% of the length of two extended alkyl chains. Figure D shows reversed or inverted MICELLE. These have a water core surrounded by the surfactant, the polar head groups. The alkyl chains together with a non-polar solvent make up the continuous medium. Like normal MICELLE, they can grow into cylindrical form. In E, as you can see, a bicontinuous structure with the surfactant molecules aggregated into connected films. And the last F shows vesicles Vesicles are built from bilayer similar to those of the lamellar phase and are characterized by two distinct water compartments, one forming the core and one the external medium. Vesicles may have different shape, and there are also reverse type vesicles. In particular, let me tell you, depending on the surfactant type and on the solution conditions, spherical MICELLES can grow one-dimensionally into cylindrical MICELLES or two-dimensionally into bilayers or discoidal MICELLES. MICELLE growth is controlled primarily by the surfactant heads. Since both one-dimensional and two-dimensional growth requires bringing the surfactant heads closer to each other in order to reduce the available area per surfactant molecule at the MICELLE surface, and hence the curvature of the MICELLE surface. For all these micellar structure in aqueous media, the surfactant molecules are oriented with their polar heads towards the water phase and their tail away from it. Moving further, we will now understand the structure and composition of MICELLE. First, what will be the structure of MICELLE formed by ionic surfactants? The interior of the MICELLE, a hydrophobic core, is composed of the hydrocarbon chain of the surfactant molecule. It has a radius of approximately the length of fully extended hydrophobic chain, as you can see in the figure. Another thing, a stern layer surrounding the core is part of electrical double layer, which is concentrating shell of hydrophilic head group with 1 minus alpha bracket n counter ions, where alpha is degree of ionization and n is the aggregation number, which is the aggregation number is the number of molecules in the MICELLE. For most ionic MICELLES, the degree of ionization is between 0.2 and 0.3. That means 70 to 80% of the counter ions may be considered to be bound to the MICELLES. The Gouy-Chapman portion of electrical double layer is diffused and surrounds the stern layer. It contains the n counter ions required to neutralize the charge on the MICELLE. The thickness of the double layer is a function of the ionic strength of the solution and is highly compressed in the presence of electrolyte. See the diagram where it shows the structure of MICELLE formed by ionic surfactants. Let us now turn to structure of MICELLE formed by non-ionic surfactants. Here, firstly, the structure is essentially the same, except the counter ions are not present in the outer region, but rather coils of hydrated polyethylene oxide chain. Secondly, They are larger than their ionic counterparts and may sometimes be elongated into an ellipsoid or a rod-like structure. Thirdly, they have a hydrophobic core formed from the hydrocarbon chains of the surfactant molecules surrounded by a shell. This shell is called the palisade layer. This shell is composed of the oxyethylene chains of the surfactant, which is heavily hydrated, as you can see in the figure. Another important characteristic of MICELLE is that the aqueous phase penetrates into the MICELLE beyond the hydrophilic head groups, and the first few methylene groups adjacent to the head are considered in the hydration sphere. Therefore, we can divide the interior region of the MICELLE in an outer core, which is penetrated by water, and in an inner core, completely water excluded. After learning the structure of ionic and non-ionic, let us turn our attention to the structure of MICELLE in a non-aqueous solution. MICELLEs formed in a non-aqueous solution, which we already know they are called reverse or inverted MICELLes, have a core composition of the hydrophilic groups surrounded by a shell of the hydrocarbon chains as shown in the figure. Based on the geometry of various micellar shapes and the space occupied by the hydrophilic and hydrophobic groups of the surfactant, it is possible to estimate the structure of a MICELLE. It is high time now we will summarize whatever we have learned in this module. Number 1, MICELLE is an aggregate of surfactant formed when the concentration of surfactant in solution is above the critical MICELLE concentration. In an aqueous solution, MICELLE is formed where polar or non-ionic head groups form an outer shell and non-polar hydrophobic tails are sequestered in the interior. In non-polar solvents, as we learned earlier, hydrophobic tails are exposed to the solvent while polar heads point toward the interior of the aggregate, which are called the inverse MICELLE. The process of micellization, as we learnt, depends on the balance of intermolecular forces, that is hydrophobic, steric, electrostatic, hydrogen bond and van der Waals interactions. CMC is the exact concentration at which an aggregate becomes thermodynamically soluble in aqueous solution and can be detected as inflection point when physico-chemical properties are plotted as function of concentration. Structure of MICELLE formed by ionic surfactants is composed of hydrophobic core formed by hydrocarbon chain. Secondly, an electrical double layer divided into Stern layer and Goy-Chapman layer. Stern layer is composed of hydrophilic head group, whereas Goy-Chapman layer counter ions that neutralize the charge on the MICELLE.